Hello, welcome to the new lecture in algorithm series. In this lecture we will be discussing how a variable substitution method can be used to transform a complex recurrence relations into simple recurrence relations. So as we know, the common recurrence relations can be solved by using a recursion tree or a master's theorem result, but some recurrence relations which has subproblems of square root of n or cube root or log n may not be directly solvable by using a recursion tree. An example, if t of n is equal to t of square root of n, here the subproblem is of size square root of n plus f of n. Now how to solve recurrence relations of this form? For that we are going to use a simple trick of substitution, a variable substitution. We'll substitute n by e power x. So substitute n by e power x, then t of square root of n will becomes t of e of x by 2. Now once it is in that form, t of e power x equal to t of e power x by 2, once it is in this form, then it can be transformed into a simple recurrence relation. So let us consider one example solving recurrence relation t of n equal to t of square root of n plus c. This is c is constant, and the base case t of n equal to 1. Okay, now apply this trick of substitution. N is e power x, then square root of n is e power x by 2, then it will be transformed into t of e power x is equal to t of e power x by 2 plus c. Suppose if we define a new function s of x, if we take s of x as t of e power x, then t of e power x by 2 can be written as s of x by 2. So we define a new function s of x as t of e power x. So s of x by 2 is t of e power x by 2. So from that we can write this function as s of x plus s of x equal to s of x by 2 plus c. Now we can see that this recurrence relation s of x equal to s of x by 2 plus c is in the known form. You can easily see this is a recurrence relation that we got for the binary search problem. So for the binary search problem, and this is log x, so you can easily argue by taking up to k levels, then you get s of x by 2 power k. So as it is k levels, k into c, and as you know that k is log x base 2, so log x base 2. Now the time complexity, so the time complexity is also order of log x, because this is order of k. Now we have to find out for t of n. So as we know that t of e power x is s of x, and we also know that e power x is n. Now from that you can get x as log n base e. So s of log n base e we have to find out. S of log n base e is big O of log of log n base e. Okay, so we got the time complexity t of n value for this problem. So this is how a simple substitution n as e power x we can solve by converting into a simple recurrence relation. So let us consider one more example. where we have t of n as t of square root of n plus n. So we have here, instead of a constant term, we have n here. If you substitute n as e power x, then the similar thing, you get t of x as t of e power x is equal to t of e power x by 2 plus e power x, and you consider same s of x as t of e power x, then s of x by 2 is t of e power x by 2. So then from that you can write s of x is s of x by 2 plus e power x, and this also, if you solve and e of x becomes a dominating factor, e of x is greater than e of x by 2, e of x by 2 is greater than e of x by 4, and so on. From that you can write this as big O of e power x, and s of x is big O of e power x by using a simple, again as we know that t of e power x is s of x and e power x is n. From there x is log n base e. Okay, so s of log n base e is big O of e power log n base e, so e will cancel, so you get order of n. Okay, so this is how the complex recurrence relation can be solved by using a simple variable substitution. Now there are two homework problems. The first problem is t of n is t of, this is ath root of n or n power 1 by a plus 1, and the base case t of b equal to 1. And similarly we have t of n is 2 into t of square root of n plus log n. This is a textbook example, a textbook exercise problem, sorry. So these two are homework problems. Now whatever the method that we have discussed, that is a variable substitution method, which effectively transforms the complex recurrence relation into simple forms. And also, if you had observed that f of n is a dominant term which plays a crucial role in finding the final complexity. In the first case it is the c term which is repeated k, so that's why we got k. And then the second example, e power x. Okay, thank you.